Hi, everyone. Welcome back to MAT1841. This is the last of the various lectures. As I mentioned before last time, I'm just talking about various topics that I care about, things that I've done. This material will not be on any PSETs. All the PSETs have already been assigned and are due like today. So, okay, let's go ahead and get started. So I'm going to talk a little bit about secure federated count queries. So this is another application of some of the probabilistic sketching we've done, but I'm going to pair it with some homomorphic encryption to allow you to show how you can combine these various tools together to build a secure way of querying across hospitals. So what do we mean by that? So suppose you have a bunch of hospitals. Hospitals here are going to be blocks. Suppose you have hospitals A, B, and C, and you have some question. You might ask, how many patients are diabetic across the entire set of hospitals? Or things of that sort, or how many patients have hypertension and are between the ages of 19 and 29. And so you might ask these questions, and then what you do is, well, in order to figure out how many patients are at all these hospitals, you have some number, say X1, X2, X3. So these are the sets of patients at each hospital that fit some criteria. And then what you really want is you want to know the size of the union of these three sets. Okay, so that's what you really want to know. And of course, there are very complicated questions that you can ask at this. If there's only one hospital, of course, it's just a database problem. You look at your database of patients, and then you're like, well, how many of our patients have this condition? And you report that number. So that's really easy. But when you have multiple hospitals, this is a little bit more complicated because you need to have some query party that's asking each of these hospitals this question. They return some information, and from that information, you need to compute this value here. Okay, and so there are a couple ways you can do this. Let me formalize a little bit more. So we have this distributed clinical query. So a little bit more formally, we have a network of hospitals. So there are a network of hospitals. Let's call these H1 through Hn with limited communication. And when we say limited, we mean both limited in a couple of different ways. One is that they're limited in the amount of information they may be able to send to the other hospitals or to send to each other. And the other way is that they may be limited is more legalistic. So in terms of the privacy of the patients that are involved. And so obviously, if you had unlimited communication between the hospitals, you could just merge them all into one big hospital database system and then send your query, and then you would figure out the union of all these different sets. But now, of course, if you don't have unlimited communication, that's a little bit more difficult. Because and so there are a couple different ways we can approach this. And as you guys might guess, the approach that we're going to eventually end up using is going to be related to the probabilistic sketching. So log counting, hyperlog, those kinds of things. But then we're going to pair it with something else to ensure actual patient privacy. But first, let's set this up a little bit more. Let me give ourselves a little bit more notation first. So let X1 through Xn be the set of all patients of interest, be the sets of all patients matching some query. Okay, so X1 is going to be the patients at hospital 1 that have hypertension, for example. X2 is going to be the set of patients at hospital 2 that have the same property. And what we want is we want to compute this union. And so let's let just big X be equal to the union, X1 union through Xn. So that's what we care about. We care about the cardinality of this. We don't actually care about the X itself. We only care about the number of patients that match this. There are, of course, other types of queries where you actually want to get the entire list of patients. But in order to do that, well, you can't really get that much privacy. Well, there are ways of getting partial privacy for that, but we're not going to address that question. Let's see. So what's an initial really stupid idea? Like you want to communicate a very small amount of information between the hospitals and get some proxy for the size of this union. Yeah, exactly. So this is a really stupid protocol, but it is actually what many hospital query systems do. It's very cheap, it's very simple, and it's pretty easy to show that it preserves some amount of patient privacy. So the initial idea is you're just going to estimate the size of X is approximately equal to the sum over all I of the size of Xi. There are a number of pros of this. So The biggest pro is that this is easy to compute. This is super easy to compute and send. Very little data is sent. And so we can give some guarantees on privacy. We're not going to go into that too formally, but basically, if you send less data, you're preserving privacy more for your patients. And yeah, so this is relatively private, and that can be quantified, although we're not going to do it. Of course, there are some cons here. The biggest con is that the size of the union is not actually equal to the sum of these things, and so this is not quite accurate. So note that this is actually what many hospital systems in practice do, which is they send just a single number referring to the number of patients they have at MAT1841 query, and then the central server sums them all together and returns that as the answer. Often you will add a little bit of noise to it just to add a little bit more privacy. So like maybe if a hospital were to send back the number 1, that would be revealing too much because that would reveal that only one of its patients has hypertension. So you do sometimes add a little bit of jitter, a little bit of deliberate noise to the system to have slightly better privacy guarantees. But by and large, this is one of the standard ways that hospitals share information. You just share these raw accounts, and that's relatively safe. Okay, what's the opposite kind of really naive idea? Well, we already talked about it a little bit. Now, the opposite idea is to do full data sharing. So, of course, this completely ignores the problem of communication and privacy. Just send your entire database in a truck or on the internet or whatever to a central party. They combine them all together, and you do your query there. So this also works pretty well. So send all xi to central party to compute union. Okay, and let's have some pros. The biggest pro is that it gives you the exact answer. In fact, it's pretty easy to show that you basically have to do this. You basically have to send all this information if you want an exact answer. There's no real way around it. You can do things to obfuscate the answer, but you do need to send something that contains the information of all your patients if you want an exact answer. And of course, the big con is, well, there's risk to privacy if the central party is compromised, or if it gets intercepted in transmission or anything like that. So this just, by nature, it has a higher risk of privacy because you're revealing more information that leaves the boundaries of a hospital wall. So this is another common solution. So this is, the hospitals do this. You need to have all sorts of data sharing contracts, and it's quite the process, but this is one of the other standard ways that, okay. Yeah, this is one of the other standard ways that hospitals share information for things like clinical queries. And this is what you do when you need more accurate responses. In practice, you actually send hashes of the patients. So instead of sending the actual patient IDs, you send some hash of it, and it gives you some sort of obfuscation, but it doesn't give you that much protection because, of course, the set of possible patient IDs is known. So you have a health card number or social security number or social insurance number. So like, it's not really a protection against dictionary attacks, but it provides some amount of obfuscation at least. And sometimes it decreases the amount of data that needs to be sent. Okay, so those are the two sort of naive protocols. Let's talk a little bit about the more private solutions for this kind of thing. So let's talk about secure protocols. And what secure means, of course, varies depending on your threat model and what exactly you're trying to do. But these are basically, there are a number of different ways you can approach this. And the mathematical problem that we're approaching here is called the private set union. In our case, we're calling private set union cardinality because we only want to know the number of patients. We don't actually care about which patients those are. So we want to know the total number of patients that fit some set of criteria across the hospital. And so this is the private set union problem. And we're going to use a couple ingredients here. So what are ingredients going to be? Well, for one, we're going to be making use of encryption. And I'm going to go through some very basic encryption protocols, though we're not going to go into that in detail because this is in the crypto class. But the basic ingredient, one of them is you have some hard math problem for encryption. And here we're going to describe the discrete log problem, since this is nice and easy to understand. So if you're given some x to the k over a finite field of a prime order, finding k is hard. Okay, so it turns out that, well, of course, you can just try a bunch of different k's, but for large k and x and sufficiently nice p, this is a known to be hard problem. Known to be hard if P satisfies a couple of properties. So if P is a prime such that 2Q plus, such that it's equal to 2Q plus 1, where Q is another prime. Okay, so this is a highly technical condition that arises from number theory, which we're not going to discuss. But basically, we have some hard math problem, and then you can use this to construct an encryption algorithm that allows you to send information securely. And so long as this problem actually is hard, then you don't have to worry about an adversary learning information from these encrypted data points. The other piece that we're going to use is we're going to use something called a one-way hash function. So this is going to be slightly different from the hash functions that we've been discussing as sort of randomized hash functions, because with randomized hash functions, what we cared about was that the construction allowed us to take nice probabilities. And so we computed nice expectations, nice moments, and things like that. Whereas a cryptographic one-way hash function basically posits the existence of a function f such that taking the inverse is difficult. Okay. So we're going to posit the existence of these things. So one is a hard math problem. We're going to, like I said, we're going to use the discrete log for the sort of baby parts of the encryption. Although the actual implementation that we're going to discuss later uses a more difficult math problem called learning with errors. But we're not going to worry about that too much. But yeah, so now we have these two pieces. It's actually pretty easy to construct a completely private set union cardinality. And this is going to be a relatively easy solution. It's not going to be very efficient, but it's going to be based off of a paper by Clifton et al. In 2002. So this is tools for privacy preserving data mining. Privacy preserving data mining. And this was published in SIG KDD. And the key to their particular protocol is something called commutative encryption. So what does that mean? Commutative encryption? Well, that means we want commutativity of the encryption operations. So if you encrypt it with one key, and then you encrypt it with the other key, so you have some message X that you've encrypted twice, the order that you've encrypted it both times doesn't matter. So that is the basic premise of commutative encryption. And one example of this based off of discrete log is the Polig-Hellman cipher. So remember, we're going to start with a safe prime P, and encryption key. Let's call this, oh, I think I called this K. I apologize. I think my notation is going to get a little funky later on, so I reuse K for something and X for something different. So K is an FP. Then the encryption operation is going to be super simple. Encryption is going to be just X to the K mod P. And of course, as you just said, the assumption is that reversing this operation is hard. If you don't already know what K is, it's hard to reverse this operation to get X. Okay, so then what's the protocol going to be? So all hospitals share P, and then you encrypt them. You encrypt all of them, X in XI, using secret key KI. Okay? So basically, each hospital has some, where each X here is going to be one of our patients, patient IDs or whatever. So then hospital 1, you generate, say, E sub 1 of X1, E sub 1 of X2, through E sub 1 of, let's say, X capital N. Okay? So each of these hospitals generates these values. Well, I guess I need X sub 1, 1, because this is all for hospital 1. 1, 2, 1, N. Okay? So basically, you encrypt all your patients, and then you send those encrypted values to each of the other hospitals. And so what you do is you send these. So you send all this information. You send this to hospital 2. And what hospital 2 does is hospital 2 then encrypts it with their key. So then hospital 2 generates E sub 1 of X1, 1, but then you get E sub 2 of E sub 1 of X1, 1, and so on. And so eventually what you end up with is you end up with E sub N of E sub N minus 1 of all the way through E sub 1 of X1, 1. And you have this of all different patients. So really this is Xij. And notice that what happens is each hospital does this. So every hospital sends it all around. Every single patient from each hospital gets encrypted n times. But of course, this encryption is commutative. So the order in which the encryptions happen doesn't matter. And then what happens at the end is you have all these encrypted values that, and since this is a deterministic encryption, what happens is then you can just remove the duplicate IDs, right? So if the hospital 1 and hospital 2 had the same patient, after all these rounds of encryption, they're going to they're going to know that that patient was in both hospitals, and then you can remove that as a duplicate. And so then all you have to do is then you have all these things that you can't easily connect back to the original patient IDs, but you can still say, oh, well, I can deduplicate these sets of encrypted IDs and just count the total number of encrypted IDs. So at the end, encrypt using and then send to be encrypted by everyone else. Encrypted by everyone else using their secret keys. Else using their secret keys. So the secret key KI is the power. Oh, so secret key KI is yeah, so that's the power that you're taking X to. And so obviously you'll know this very easily why this is commutative, right? Is because if you take X to K1 and then K2 versus K2 then K1, you get the same value. And that's the basic premise for the sort of commutative encryption. But yeah, so at N, we can deduplicate encrypted IDs to get unique count. Okay, and this is kind of slow because of course this takes O of n times the sum of xi in complexity. Because of course everyone's entire patient sets have to be encrypted n times by each of the hospitals, and then you need to do a deduplication operation. Even more importantly though, this requires n rounds of communication, which is slightly painful. Okay, so it's just a lot of complexity. And also, this still doesn't protect all your information because it does still reveal the each of the magnitudes of your xi's because that's how many things you sent across. And so for that reason, this doesn't provide perfect protection, but it does provide reasonable amounts of protection. It provides as much protection as sending just the cardinalities, while at the same time allowing you to get the exactness of this answer here. So you get an exact answer, but you don't have to worry about revealing too much in terms of privacy loss. Okay, and then it turns out that this is, if you want an exact protocol, this is bad, but it's not really that bad because an exact protocol, of course, it has to check every single patient, so it can't possibly be faster than order of the number of patients you have. In order to get any sort of speed up, like in our sketching section, you really do have to approximate. And the other thing I should mention is that the error isn't really that big of a deal in medical informatics because patient matching itself is already really error prone. So when you go to a hospital, it turns out that if you give your name slightly wrong, they enter your name wrong, they enter your date of birth wrong, or whatever, or they enter your health card ID number wrong. Like there are just all sorts of issues with matching patients. Like a lot of people have worked really hard on this, but there's some amount of inherent error in the system. Or maybe you broke your toe, but the nurse that was charting you said that you broke your finger instead. So there are all sorts of errors already, and so a small amount of error isn't that big a deal, and that's what we're going to have to put up with if we want a better protocol than basically what we just described. Okay, and in order to do this, we're going to use an even stronger form of, a more powerful formalism known as homomorphic encryption. So with commutative encryption, what we have is just you can encrypt it multiple times, and the order of the encryption doesn't matter. Commutative homomorphic encryption is even stronger, or I mean, it's not stronger, it's different. It gives you a different guarantee. That turns out to be quite helpful. So with homomorphic encryption, what you have is you have some operation that whether you do it in the plain text before you encrypt, or you do encrypt it first and then do your operation, you get the same answer. So basically, you have some plain text space. So if you take, let's use D to refer to our decryption operation. D of E of AB, where we both all these together, is equal to D of E of A times E of B. Okay, and so this would be something that's known as multiplicatively homomorphic. Multiplicatively homomorphic. Okay, and what this lets us do is it allows you to do computations on encrypted data. And this is super powerful because then this preserves a lot more privacy since all your computations happen in this encrypted space and no one knows what's going on until you decrypt it at the end. I should also mention that there's another form of, you can have homomorphic encryption for different types of operations. So one easy one is multiplication. Another easy one would be addition. So D of E of A plus E of B. So you can also have things that are additively homomorphic. Additively homomorphic. Basically, all you have is you have some binary operation that corresponds, that you can do either in the plaintext space or in the ciphertext space. Other operations also work, like XOR operations are another very common one. But basically, you have some mathematical operations that you can do either in plain or ciphertext. If there's only one homomorphic operation, so if only one homomorphic operation, for example, just addition, then this is only partially homomorphic. And if you can evaluate both addition and multiplication, it turns out you can show that that allows you to evaluate any circuit in theory, both addition and multiplication. Then it's fully homomorphic. Now, it turns out that we do have fully homomorphic crypto systems. So in theory, you can evaluate any function you want in ciphertext. Unfortunately, it can be rather slow because although in theory you can evaluate it, sometimes the circuits are really long and they just are super time consuming. And so you still have to do some work in trying to reduce the amount of computation that you need for this. But let's first see how we can use even a partially homomorphic crypto system. Let's just say an additively homomorphic crypto. Let's use a partially homomorphic crypto system with distributed keygen to show that we can compute the summation version up here. Wait, where was it? The summation version up here without revealing any of the individual counts. So obviously this is, that's to be expected. That's the whole point of homomorphic encryption, is that you can compute that. But let's see what actually happens for a particular crypto system, just so that we see some of the details. So I'm going to call this MPC sum for multi-party computation of the sum. So we can use an additively homomorphic crypto system, homomorphic crypto system. And the important thing here is we need to have a distributed key generation. Because it doesn't help to do everything while encrypted if the bad guy has access to the encryption key, or sorry, to the decryption key. So what we're going to do is we're going to make use of a public-private key crypto system, and we're going to ensure that no one has access to the secret key. And so only with cooperation of all the parties can you decrypt anything. And so then you don't have to worry about the intermediate data revealing stuff because everyone has to cooperate in order to decrypt any of the ciphertext. And for this example, we are going to use a crypto system by El Gamal from 1985, which is a fairly well-studied crypto system. And so let's describe it a little bit mathematically. So if we let P be a suitable prime, oh, I should mention for the sake of completeness that these sorts of operations, I'm talking about everything in terms of finite prime fields, but there are other groups on which you can do these sorts of operations. And so often you may have heard about people using elliptic curve cryptography and doing sums on points on elliptic curves. And that is a more modern way of doing this, but it's a little bit harder to write down. And so I'm just going to continue using a finite field of order P. And let's say we have G in FP, a generator of quadratic residues, mod P. Okay, this is an important technical condition, but we're not going to go into too much detail because that would be a cryptography class. Such that Q is congruent to X squared. Okay, like I said, technical crypto details, which are very important, but something that we aren't really going to worry about because we're just using these crypto systems as other people have built them. So now a private key X in, oh, this is where I started messing up my notation. I'm going to use X to be my private key now instead of K, and I apologize. So we have a private key and we have a public key. And our public key is going to be Y is equal to G to the X. Everything here is working in the finite field, of course. And so this is, from the public key, you cannot easily compute the private key. Because of course that's a discrete log problem. And so now given a message M, M has to be a quadratic residue, but we're going to sweep that under the rug for now. So given some message M, we're going to say that the encryption of M is going to be equal to G to the Z, comma, M Y to the Z. Okay, so it's going to be a tuple, where Z is a random number. Okay, and what we're doing basically is this sort of encryption is no longer deterministic. It has it's probabilistic, which means that when you're doing this encryption, if you encrypt the same number multiple times, you get different values. And so this way, this sort of crypto system isn't subject to a dictionary attack because you can't just try encrypting and seeing if the ciphertexts are the same. And so this is a useful property for what we're trying to do. And so we have some encryption, which is this operation, and we have some decryption of a pair of C1, C2, where it's going to be equal to C1 to the X to the P minus 2 times C2. And note that this is, so note that X to the P minus 2 is congruent to X to the minus 1 by Fermat's little theorem. And because that's the case, this decryption actually does work. So decryption of this encrypted value for any random value Z, when you plug that in, that's going to be G to the XZ times P minus 2 in the exponent times MY to the Z. But of course, G to the XZ, P minus 1, is then just going to be equal to Y to the Z times Y to the minus Z times My to the Z, which is equal to M. Okay, so basically this is so basically we have some crypto system, we have some encryption algorithm method, and we have some decryption method. And what we can do here with this crypto system and with many other crypto systems, but we'll show it in this case, we can distribute the key generation. So it can distribute key generation. So no hospital has the private key. Has private key. And the way we're going to do this is we're going to have hospitals which are each going to generate a sort of partial private key for themselves. So they're going to generate our XIs privately. And then we're going to broadcast that. You're going to broadcast the partial public keys. We do the XI, partial public keys. And then the final public key is just going to be Y is equal to the product of all of our YIs, which is going to be equal to the product of all of our G to the XIs, which is of course going to be equal to G to the sum of our XIs, which would be our public, where X equal to the sum of all the XIs is the entire secret key. But of course, no one party has that. So we have a public key that is shared between all the parties, and a public key that everyone knows, and a private key that's broken up into pieces. And so no one party can decrypt. In order to decrypt, you need to have all of our hospitals coordinate together. So for decrypting a value, let's say C1, C2, since the ciphertexts are come in pairs, each hospital receives C1 and broadcasts C1 to the XI. So they broadcast some partial decryption based off of their private key. which the server combines, central party combines to get C1 to the X. Okay, and now after we do this, so this is just talking about how we do this, so partial QGen. Then we just have to encode our problem. Well, let's just let mi be equal to, let's say some value. Let's say this is 4 to the xi. Okay. I chose 4 for complicated reasons. You don't want to choose, but it doesn't really matter. So we have some encoding where we encode each of our values as an as a power. Then we know that E of mi is going to be equal to G of zi, 4 to the xi, y to the zi. And then the product of all these is going to be, of course, equal to G to the sum over our zi's, E to the, sorry, not E, 4 to the sum of our xi's quantities, and y to the sum over our zi. Sorry, these are big x's, not little x's. And of course, then when we decrypt, so when we decrypt this product, that's going to be equal to 4 to the sum over our xi's. And we can use that to learn the, allowing hospitals to learn the sum, learning sum without revealing individual pieces. Okay, any questions about all that? So the basic idea here is with clever crypto and a partially homomorphic crypto system, you can do better than just like sending the sum, sending the counts. You don't even have to send those in plain text. You can have some protocol that sums them together using homomorphic encryption. But now this only gets us so far, that only gets us this case. What we really want is something that's closer to actually getting this union cardinality, right? We actually want this union cardinality. And we had some protocol to do it, but that was really, really expensive and still revealed the individual counts. So what we're going to do now is we're going to turn back to probabilistic sketching and show that we can use these homomorphic algorithms in a efficient way to compute the union of probabilistic sketches. So this is going to, let's call this MPC hyperlog log sketch. And let's say we're using Elgamal, but really you can use any partially, or not any, but there are many different choices you have of a partially homomorphic crypto system. So now recall a hyperlog log sketch. There are a bunch of properties. This is Flageolet et al. In 2008. And so what you do is you start by pseudo-randomly partitioning X. So we're going to only consider a single set X now. Partition X into buckets, B1 through BK via a hash function. So here, again, we're working with pseudo-random hash functions as opposed to cryptographic hash functions. H1 from U to K, though in practice, many people just use a single hash function for all of it. So we do that, and then we let mi going to be equal to the ceiling of minus log of the minimum over X in Bi of H2 of X, where H2 is a random hash function onto the unit interval. Random hash function. Okay, and then the property of hyperlog log is, of course, that the cardinality of our set is approximately equal to this complicated formula. AK, k squared x, where AK is something complicated. It's equal to k times integral from 0 to infinity of log of 2 plus u 1 over 1 plus u to the k du inverse. But note that nowhere in there is our counts. And so these AKs are pre-computed. And our Z here is equal to the sum over J equal 1 to K of 2 to the minus M of J. So remember, these were our bucket values. Oh, note that that was just a complicated way of saying the position of the leading one. So that was just a complicated way of saying that that value is 5. So we saw this with our cardinality estimators back when we were talking about sketching. So our Z here is going to be the harmonic sum of these things. So, sorry, harmonic mean. And then once you do this, the estimator has about 1.04 over root K relative error. Okay, so now the question is, can we combine hyperlog-log sketches homomorphically? And the answer is yes, or I wouldn't be given with this talk. So can we combine hyperlog-log sketches homomorphically? And this is something that I did in a paper in 2020 with Griffin Weber. And so we used a very simple solution for this. There are a number. I should note that there are a number of ways that people have done this before, and so there are a number of different solutions. This is only one of them. But our solution was pretty simple. We're just going to write each hyperlog-log bucket, let's say m of I, and we're going to assume that each of these buckets is in some defined interval. So let's say between 1 and 64, because well, with a 64-bit number, your hyperlog-log bucket is going to be between 1 and 64. We're going to write this in unary with random ones. What do I mean by this? I mean that the 5 is going to be encoded as a random number, another random number, 3, 4, 5, and then after that, 1s for the remainder. And you notice that when I do this, each hospital then encrypts with a public key. Each hospital encrypts with public key entry-wise. So you got E of R, 1, 1. Oh, sorry, E of 1. And this is one of the reasons why it's super important for us to have a probabilistic encryption, because you're encrypting the same value of 1 over and over again, and you want to make sure that that's not deterministic, or an adversary would just be able to look at encryption of 1 and figure out what it is. But since this is a random probabilistic encryption, you can't do that. Well, then what you do is we combine vectors homomorphically, by multiplication. And remember, if we're working with El-Gamal, it's multiplicatively homomorphic. So when you do this, what happens is if you have a 5, that's R, 2, 3, 4, 5, 1. And let's say you had a 2, that's going to be R, 1, 1, 1, 1. When you multiply these together, what you end up getting is R, 3, 4, 5. Because of course a random number times a random number is some other random number, and you end up with this thing, which gives you 5. And so what you get is this is equal to the max of 2 and 5. So we're able to combine these hyperlog-log sketches because we've turned, using this unary encoding, we've turned this maximum operation into a multiplication operation, which we can do pretty easily in our homomorphic framework. Of course, these are all in ciphertext, so you don't actually see this happening until you decrypt at the end. So then the decrypted vector gives the maximum m of I by the number of random values. So note that you do still have to decrypt to get the number of things in the bucket, because there's no way for us to test whether something is random easily in this homomorphic framework. But what happens is that all that is revealed is the combined hyperlog-log sketch. Revealed is hyperlog-log of x. So like if you have different pieces, each hospital creates a hyperlog-log sketch of x1 through xn. You can homomorphically combine them and get the hyperlog-log sketch of x, which is just the union of the entire set. So now this is imperfect privacy, because what you're doing here is you're still revealing the hyperlog-log sketch of the entire of all the patients at the hospitals, all the hospitals that match some criteria. So you can quantify the amount of privacy loss, which we did in another paper. But what I want to talk about is instead, well, this was just using partially homomorphic encryption, right? So you only had one operation. But of course, if you have two operations, say addition and multiplication, maybe you could do better. Maybe what you could do is, right now, all we're doing is we're hiding the part of combining the union, of taking the union of these hyperlog sketches. What we're not doing is we're not actually hiding this computation. So that's the point, right? So we're taking a union of sketches, and that's hidden, but the union itself is not. And really what we want at the end of the day with these protocols is just to give the final count. We don't want the intermediate data, any intermediate data to be visible. So now the question is, can you write all of this into the homomorphic encryption framework using just addition and say, using just addition or using just multiplication? It's obviously impossible. Can you do something like this if you have both addition and multiplication? And the answer is yes, but you'll notice that you have some really ugly things here, like taking inverses, taking fractions, and those things are hard to approximate with multiplication and addition. You can do it, but it takes many, many more operations. And so instead, we're going to do something slightly different. So we're going to use a fully homomorphic encryption. So this is going to be MPC, federated approximate count. Count using fully homomorphic encryption. And this is a paper we just submitted. Layton U 2021. I mean, it's not accepted yet, so who knows what will happen. And instead of using Elgamal, which is sort of older crypto system, we use a modern fully homomorphic crypto system based on ring learning with errors. Crypto system that allows both addition and multiplication. So unlike the previous crypto systems, I'm not actually going to define the math because that would take an entire lecture. These are much more sophisticated systems. But it does allow us addition and multiplication. And that's all we really care about here. And the other part is, even though we get multiplication and addition, it's still a little bit difficult because this operation here, this harmonic mean especially. So this harmonic mean is hard to approximate using just additions and multiplications. But luckily, it turns out that when people were working on a hyperlog log, they came up with this harmonic mean to replace something earlier. So the very basic systems, if you think back to when we were starting with building these sketches, we didn't do fancy stuff like this. We just took some like average of things, and that sort of worked out. It turns out that the earlier versions of hyperlog log, the log logs, used a much simpler estimator. It didn't get quite as good of error because the estimator was just had higher variance, but it was just a simpler estimator, and that simpler estimator turns out to be a lot easier to compute. So let me write that out. So we're going to replace the hyperlog log estimator with older log estimator. Log estimator, which just uses a simple arithmetic mean. And arithmetic means are nice because we can basically compute an arithmetic mean with just summation, and then the mean part of it doesn't matter because we're dividing by the total number of parties, and that's known. And so we can compute the summation in our crypto system and then just reveal that number, which doesn't give you any other information because that's deterministically related backwards and forwards to the actual count at the end. So the estimate here that we're going to actually be using is E is equal to the A to the M times 2 to the 1 over M times the sum over I, M of I. So note here, this here is an arithmetic mean. And then we take a power. So you take the mean and then the power, as opposed to up here, where you were, oh, sorry, where was that? As opposed to up here, where you were taking these powers and then the sum. And so the order of operations matters a lot here. Because what we can do is we can combine, take the sum in the crypto system, and then do everything else in plain text, and we're still fine. Where AM has some complicated form, it's a gamma function of minus 1 over M times 1 minus 2 to the 1 over M over natural log of 2 to the minus M. But note that, of course, that doesn't have any dependence on our actual values. This is some constant that's pre-computed, where this is, of course, just the gamma function. Okay, so you can basically ignore this since this is all pre-computation, and the important step's just right here. Okay, so now this is easier to work with because we have access to addition and multiplication, and here we're just basically using lots of additions. So we do a similar strategy. So we again write each bucket in unary, but instead we're going to use a slightly different unary encoding. we're going to have zeros, say 5 zeros, and then a bunch of ones. And then what we're going to do is we're going to combine vectors again via multiplication. And note that we'll need log n of these to combine the vectors across all the hospitals, right? Because if we have n hospitals, you can do a binary multiplication tree, and that all works out. Of course, 5 here is 1, 2, 3, 4, 5, 1, 1, 1. And 2 here is going to give you 0, 0, 1, 1, 1, 1, dot. Combine these, you get 0, 0, 0, 0, 0, and then a bunch of ones. And of course, this is just the max of 5 and 2. But now, importantly, since we also have subtraction, or sorry, we also have addition. Since we have subtraction, we can do something slightly. We can combine these in. We can count the number of zeros in ciphertext. So subtract from 1, and sum within the vectors. So that gives you 1, 1, 1, 1, 1, and then a bunch of zeros. And of course, that just gives you 5 while still encrypted. So we can do all those operations while staying encrypted, and we end up, and of course, we can sum together all the buckets. So add together all buckets to then get the sum over all the buckets. And that is, of course, the value that we need to enter into our estimator layer. And so we just reveal that number. So we do a distributed decryption of that number. Distributed decryption to get a proxy for a final approximate count, revealing no other information other than this proxy for that count. I go straight into this formula, and yeah. This is just one of the ways that you can combine together some of what we've learned with probabilistic sketching to make algorithms work more efficiently in other contexts. In this case, you can think of sort of operating in this encrypted space as some other architecture you're targeting. And you can make use of these clever probabilistic sketching to decrease the computational load on these sorts of private distributed encryption algorithms. And I think I will end there. So this was just another one of the sort of lectures on ways you can apply some of what we've learned in this class to other settings, in combination with other tools, of course. Okay, that ends class. I look forward to seeing all of you guys' presentations tomorrow and, tomorrow and Friday and next Wednesday. So I think I mentioned in an email, please let me know if you're planning on presenting via the Blackboard or via slides. Because I will need, if you're presenting via slides, then I'll just ask you to join the Zoom call as well, so that everyone can see. If you're presenting via slides, then I will need to record you, and so you should let me know so I can be sure to have all the equipment set up. Any questions? Okay, well, thank you all for coming to this, optional lecture. This is not going to be assessed, and I look forward to seeing all your presentations. See you all tomorrow. Bye.